The night scene that follows is a reconstruction of how discoveries beneath the sea often begin. Far from the nearest coast, a survey vessel moves at walking speed across black water. Its engines hold a steady note. Above the bridge, the sky is empty. Below the hull, the depth increases until sunlight has no meaning. Inside the control room, the ocean is being drawn one narrow strip at a time. Lines of color spread across a monitor as sound leaves the ship, reaches the seabed, and returns. Most of the display is familiar: soft slopes, scattered rock, channels filled with sediment. The technicians have watched similar patterns for hours. Then a shape enters the screen that does not seem to belong. A long ridge appears first. Another runs beside it. Between them lies a flatter space, bordered by shorter lines that meet at angles. Farther east, a raised platform rises from the surrounding bottom. The arrangement is incomplete, blurred at the edges, and partly hidden beneath mud. Yet when the map is shaded, the ridges begin to resemble walls. The open areas resemble courtyards. A curved depression could be a harbor, or perhaps the remains of an ancient river bend. No one in the room says the word city. That word carries too much weight. It can turn an uncertain pattern into a conclusion before the evidence has arrived. The vessel continues along its planned course, but the coordinates are marked. Hours later, the ship turns and crosses the same ground from another direction. If the first image was caused by interference, the pattern should change. If it was created by an error in the ship's movement, the angles should drift. Instead, the long ridges return. The platform appears again. Several boundaries remain in almost the same positions. One of the technicians leans closer, not because the map is clear, but because it is clear enough to be dangerous. The new pass also shows something the first one missed. One apparent wall does not end at the visible seabed. A weaker signal continues beneath the sediment, suggesting that the feature may extend into a buried layer. That discovery can be read in two opposite ways. It may be evidence of an older structure concealed by later deposits, or it may show that the supposed wall is simply part of the natural geology below. Then another map is placed over the survey. It is not a map of the modern sea. It is a reconstruction of the coastline during a time when immense quantities of water were locked in ice. The modern shore moves outward. Broad plains rise from the blue. Rivers continue across land that is now submerged. The coordinates of the anomaly fall within one of those vanished landscapes. For thousands of years, this place may have faced the sky. Animals could have crossed it. Rivers may have carried fresh water through it. Human groups may have camped nearby, followed the shoreline, gathered food, or marked places that mattered to them. None of this proves that the ridges were built. It proves only that the location was not always beyond human reach. And this is where the mystery truly begins. The sonar has not photographed streets or temples. It has recorded returning sound, processed by instruments and arranged by software. Yet the pattern repeats, and the ancient coastline gives it a setting in which human activity was possible. The sea offers no helpful label, only distance, pressure, and a quiet surface that conceals both ruins and ordinary stone below. The vessel moves onward, leaving the coordinates behind. On the monitor, the shapes remain suspended in artificial light, too organized to ignore, too uncertain to name. Before anyone can decide what lies beneath the mud, a more basic question must be answered. How does sound become a map? And at what point does a map begin to look like architecture? To understand what appeared on the monitor, it helps to forget the image for a moment and listen to the process behind it. Sonar does not open a window through the water. It sends a pulse into darkness and waits for an answer. The pulse leaves a transmitter beneath the vessel and spreads downward. When it meets hard rock, much of its energy returns quickly. Soft mud absorbs more of the sound and sends back a weaker signal. A slope changes the angle of the return. A metal object may produce a bright response and a dark acoustic shadow behind it. From thousands of these differences, software builds a picture that the human eye can read. Different systems reveal different parts of the hidden landscape. Multibeam sonar measures depth across a broad strip beneath the ship, allowing researchers to build a three-dimensional surface. Side-scan sonar looks outward and emphasizes texture, edges, and objects resting on the bottom. A sub-bottom profiler sends lower-frequency sound into sediment, searching for buried layers that ordinary imaging cannot see. None of these instruments knows what a wall is. None can recognize a street, a temple, or a harbor in the way a human observer does. The machine records distance, strength, angle, and time. Meaning arrives later. This becomes clear when the opening anomaly is shown. It is a field of uneven tones crossed by bands. The suspected boundaries are present, but they do not command attention. Technicians remove noise, correct for the vessel's motion, combine overlapping passes, and adjust the contrast. A digital terrain model is created. Then artificial light is cast across it from a low angle. Suddenly the ridges stand taller. Shallow channels seem deeper. A broken edge becomes a sharp corner because the shadow beside it has been darkened. If the vertical scale is exaggerated, a low step can rise like a defensive wall. If missing data are filled by interpolation, software may connect points that the seabed never connected. These steps are not tricks. Without processing, much of the survey would remain difficult to understand. Every map simplifies reality. The danger appears when the finished image is treated as a direct photograph and the choices behind it disappear. Rotate the map and the city changes. Light it from the opposite direction and some walls weaken while other lines emerge. Remove the outlines drawn by an excited observer and several buildings dissolve into uncertain ground. Restore those outlines and the eye completes them. The first reversal of the investigation is therefore important. The audience has not been looking at ruins, it has been looking at an interpretation of echoes. That does not mean the shapes are imaginary. The returning signals came from something real. The uncertainty concerns what that something is and how much structure the human mind has added. A genuine settlement can appear in sonar data. So can a shipwreck, a quarry, fractured bedrock, a modern cable, fishing debris, or a chain of natural ridges. Confidence grows only when several methods agree. A broad depth model may reveal the terrain. Side scan may show separate blocks. Sub-bottom data may expose a buried surface. Cameras and samples may test what the sound suggested. This is why the second pass over the opening coordinates matters, but does not settle the question. Repetition shows that the pattern is not a fleeting electronic ghost. It does not show that human hands produced it. Before the anomaly can be judged, the investigation needs a comparison. What does a confirmed drowned settlement look like when mapped by the same machines? And why should researchers expect human places to exist so far beyond today's coast at all? The answer begins not with sonar, but with ice. Long before the modern shoreline was fixed on maps, the ocean stood lower, and an enormous part of the human world lay where ships now pass. The coastlines printed on modern maps feel permanent because a single human life is too brief to watch an ocean cross a continent. Harbors are built, borders are argued over, and cities rise beside the water, as though the line between land and sea has always rested in the same place. Near the height of the last glacial period, immense ice sheets covered large parts of the northern world. Water that would otherwise have filled the oceans was held on land as ice. Global sea level stood more than 120 meters below its present position. When the modern blue is peeled away from a reconstruction, familiar geography begins to change. Islands join larger landmasses. Narrow channels close. River valleys continue beyond today's beaches and cross plains that no longer appear on ordinary maps. Sheltered bays become inland basins. Low ridges rise into hills. Wetlands spread beside freshwater channels. And long corridors connect regions that now seem separated by open water. These were not useless margins at the edge of the human world. They offered what people needed. Rivers provided drinking water and attracted animals. Estuaries brought fish, shellfish, birds, and edible plants within reach. Higher ground offered shelter from floods. Stone could be collected from exposed beds. Coastal routes allowed movement between environments without crossing high mountains or dense interior forests. If people preferred such places, then a large part of their record is missing from the land archaeologists can examine. Caves and inland shelters survived because the water never reached them. Camps beside vanished estuaries did not receive the same protection. Some were destroyed by waves as the sea advanced. Others were buried under sand, mud, and later marine deposits. A few may remain intact, beneath surfaces that appear empty today. This changes the meaning of underwater exploration. Searching the continental shelf for traces of early people is not a romantic detour from serious archaeology. It follows from what is known about sea level. The question is not whether humans could have occupied some drowned landscapes. In many regions, it would be surprising if they had not. Yet another distinction must remain clear. The age of the landscape does not date every feature found upon it. A ridge may have formed millions of years before the Ice Age. A ship may have sunk there centuries ago. A cable may have been laid across the bottom last year. Even a human-made stone arrangement could belong to a later period, placed when local land movement or changing water levels briefly exposed the area. The opening anomaly therefore becomes both more plausible and more uncertain. It stood within a landscape that may once have supported human activity. That fact gives the sonar pattern a setting. It does not turn the pattern into a settlement. Still, the scale of what vanished is difficult to hold in the mind. The modern shoreline is only the latest frame in a much longer film. Entire hunting grounds, freshwater basins, crossing routes, burial places, and meeting grounds may now lie beneath shipping lanes. As the climate warmed and ice melted, seas advanced in pulses and pauses. In others, storms, collapsing shorelines, earthquakes, or sudden waves may have transformed a familiar coast within hours. That possibility gives the submerged world its emotional force. The seabed is not merely geology covered by water. In some areas, it is former homeland, crossed by footsteps that left little chance of survival. The most important discoveries may not be palaces. They may be cooking places, tool scatters, fish traps, graves, or the faint border of a dwelling pressed into ancient soil. And somewhere among those quiet traces, there may also be stone features whose purpose is not obvious. Sonar can lead researchers toward them, but only context can reveal what they mean. If entire regions disappeared, one of them should preserve more than isolated anomalies. It should contain river systems, lakes, wetlands, and hills that can be mapped as a connected country. Beneath the cold, busy waters of the North Sea, such a country has already begun to return. Before reaching it, however, the story must travel back to the world in which those plains were still alive. 20,000 years ago, the planet was not an unfinished version of the modern world. It was a complete world of its own, shaped by cold, ice, wind, and coastlines that would later disappear. Across the north, ice sheets rose over vast regions, their weight pressed into the land, and their pale surfaces reflected sunlight back into the sky. Beyond the ice, open grasslands and sparse woodland stretched across areas that now carry farms, roads, and cities. Animals followed seasonal routes through river valleys. Human groups followed food, fresh water, stone, shelter, and knowledge remembered from earlier journeys. The oceans had withdrawn from the edges of the continents. Where waves now break against cliffs and beaches, rivers once continued across broad plains. Islands that appear isolated today were joined to larger territories. Narrow seas became valleys. Shallow straits became crossing grounds. A traveler could move through landscapes that no modern person has ever seen above water. This older geography matters because it changes the locations in which the human past must be searched. Imagine standing on a hill above an Ice Age coast. The modern beach may lie far behind, perhaps beyond the horizon. Below the hill, a freshwater river curves through reeds before reaching a sheltered bay. Shellfish gather in the shallows. Animals come to drink. Driftwood collects after storms. Stone lies exposed along the banks. Such a place would attract people repeatedly. A group might remain for a few nights during a journey, return with the seasons, or build a more lasting camp. Children could learn where fish entered the channel and which plants appeared after winter. Tools might be repaired beside a fire. Food could be dried, shared, or stored. The site need not contain monuments to become important. Now allow the sea to rise across that scene. First, the lowest marshes become tidal. Salt enters the river. Storms reach farther inland. The camp is abandoned or moved uphill. Generations later, the bay covers the old hearth. Eventually, the hill itself becomes an island, then a shoal, then a faint rise beneath the water. On a modern archaeological map, the former camp may appear to have never existed. Researchers working on land will find sites farther inland, where the terrain survived. From those remains, they may conclude that people preferred caves, river terraces, or interior valleys. Yet the missing coast could once have held an equal or larger share of daily life. This is one of the quiet distortions created by rising seas. The evidence that remains visible is not a fair sample of everything people did. It is the portion that escaped drowning, erosion, and burial. The surviving map may therefore make ancient communities look more inland, less maritime, or less connected than they were. The contrast becomes strongest when present and glacial coastlines are placed together. Modern ports shift deep into the interior. Fishing grounds become plains. Busy channels close into land corridors. Vast new spaces appear along Southeast Asia, around Australia, across the North Sea, and along many continental margins. These were not empty bridges waiting only for migration. They were lived environments, changing through seasons and generations. Some routes may have guided people toward new territories. Others may have supported communities for long periods before the water returned. No single culture occupied all of these regions, and no evidence requires a worldwide Ice Age civilization. What emerges instead is a wider, more human mystery. Adaptable groups lived within landscapes that modern history barely remembers, because the boundaries of those landscapes have been erased. The sea did more than cover settlements. In several parts of the world, it concealed the paths by which populations moved, met, separated, and entered unfamiliar lands. To find those paths, researchers must look for roads that were never built from stone. Valleys, river mouths, low passes, and open plains now hidden beneath the waves, beneath miles of moving water. A road does not need paving stones to guide human movement. Long before engineered highways, people followed the easier choices offered by the land. They moved along riverbanks, crossed low ridges, passed between wetlands and high ground, and approached new regions through valleys where food and fresh water could be found. Many of those routes now end at the modern shore, but they did not always end there. Beneath the water, buried channels continue outward. Ancient rivers join valleys that once crossed exposed continental shelves. Low plains connect territories that maps now separate with blue. These are roads without walls, signs, or milestones, yet they may have carried generations of travelers. Their archaeological traces are rarely dramatic. A temporary camp might leave a thin patch of charcoal, several broken tools, animal bone, and stone flakes scattered where someone worked. A repeated fishing place might leave shell, stakes, or cut wood. A crossing point could preserve footprints only if mud covered them quickly. A landing area may have depended on boats made from materials that decayed long ago. Such remains can appear insignificant beside a sonar image shaped like a temple. Yet a single tool discovered within an undisturbed ancient soil can prove that people stood in a place at a particular time. A giant geometric ridge, without artifacts, may prove only that geology can produce impressive forms. This is the first adjustment the submerged past asks of the imagination. The earliest lost worlds may not resemble cities. They may be networks of small places connected by memory. One bank is known for stone. A sheltered inlet becomes a meeting place. A narrow crossing is used so often that knowledge of its tides passes from elders to children. When the sea rises, this network does not disappear all at once. Some routes become more valuable as dry ground narrows. A familiar river mouth turns into an estuary, then a channel too wide to cross on foot. People may begin using boats more often, move seasonal camps inland, or abandon places that had been visited for centuries. Later archaeologists see only the surviving endpoints. They find tools on one side of a modern sea and related objects on the other, then ask how the connection was made. The drowned plain between them may contain the answer, but its evidence lies under sediment, beyond ordinary excavation, or scattered by currents. This creates a misleading silence. When no coastal site is found on present land, it can be tempting to conclude that coastal life was unimportant, but absence along a coastline that did not yet exist proves very little. The places most likely to hold evidence may now be kilometers offshore. The same problem affects theories of migration. A journey shown on a modern map may look like a daring sea crossing. On an older map, it may have involved shorter passages between islands or movement along a broad coastal plain. In another region, a route that appears simple today may have been blocked by ice, desert, or flooded valleys. Geography changes the story before a single artifact is interpreted. Researchers trace submerged rivers, locate ancient springs, identify sheltered basins, and compare these features with patterns known from dry land. It is to find places where human needs and preserved sediments overlap. Occasionally, the water offers something far richer than a scattered tool. Under unusual conditions, entire occupation surfaces survive with hearths, food remains, plant material, and the outlines of shelters. These sites reveal how fragile evidence can become a detailed human scene. One such place lay beside an ancient lake rather than beneath the open sea. Its preservation showed that water can destroy a settlement, hide it, or protect it with astonishing care. It also showed why dating depends on more than finding an old object. To understand that lesson, the story must descend into the uncertain border between loss and preservation. Water is often described as an enemy of the past. It breaks coastlines, carries objects away, dissolves fragile material, and gives living organisms access to wood and bone. A site entering the sea can be pulled apart by waves before deeper water ever covers it. Imagine a small camp beside a lake or coastal river. A circular shelter stands on light poles. A hearth has burned in the same place for several nights. Seeds, fish bones, stone flakes, and pieces of cord lie close to the floor. The people leave, expecting perhaps to return after the season changes. In one possible future, a storm reaches the abandoned camp. Waves cut into the bank. The hearth collapses. Tools roll down slope, and plant remains vanish. Later currents mix the scattered pieces with shell and gravel. An archaeologist thousands of years later may find a genuine artifact, but not the place where it was used. In another future, the river changes course and lays down fine mud. The shelter floor disappears under a thin protective layer. More sediment follows before the advancing sea reaches the area. Oxygen becomes limited. The mud seals seeds, wood, and bone away from many forms of decay. What looks from above like featureless seabed may now contain an ancient surface with details still arranged around a vanished home. A third future lies between destruction and protection. The site is buried, uncovered by a later storm, moved slightly, and buried again. Some objects remain close to their original positions. Dates from the same small area may belong to different events. The result is real evidence, but its story is difficult to read. This is why preservation can never be assumed from depth alone. Deep water may protect a site from waves, yet the destructive phase may have occurred while the water was still shallow. A thick blanket of sediment may hide and preserve remains, or it may contain material washed in from somewhere else. Clear water can allow beautiful photographs while leaving an exposed site vulnerable to erosion. Ohalo 2, discovered near the Sea of Galilee, offers a rare example of what unusual burial can protect. It was not a stone city and did not need to be one. The site preserved the outlines of brush huts, hearths, plant remains, food, tools, and a human burial from a time more than 20,000 years ago. Because features and materials remained in meaningful relationships, researchers could ask not only how old individual objects were, but how people used the space. The importance of such a site lies in context. Seeds beside a hearth can suggest preparation or consumption. Charcoal within a fire area can be connected to an event. Tools found on a floor tell a different story from tools lifted by a dredge from mixed sediment. A burial placed within a known layer belongs to a human action, not merely to the age of the bone. Water helped conceal Ohalo 2 for a long period, while sediment protected fragile traces that would usually disappear on land. Its survival was exceptional, and that exception reveals what may still wait beneath drowned landscapes. A perfectly shaped ridge without a cultural layer is not stronger evidence than a modest hut floor preserved with seeds and charcoal. Size creates wonder, but association creates history. For the opening anomaly, this becomes a decisive lesson. Even if the ridges once stood on dry ground, investigators must learn what happened as the sea approached. Were deposits sealed beneath mud? Did currents bring old material from a river valley nearby? Does any ancient soil remain against the supposed walls? The answers will not emerge from one dramatic image. They require a sequence of evidence, moving from distant sound to close mapping, direct observation, secure samples, and dates tied to specific events. Every proposed underwater city must climb that sequence. The first step is easy. A shape attracts attention. The final steps are slower and far less glamorous. Yet without them, mystery can become certainty only through repetition. To continue, the investigation needs a clear ladder. Each level must ask a harder question than the one before it, and each answer must survive contact with the seabed itself. Every extraordinary underwater claim begins at the bottom of an invisible ladder. The first rung is nothing more than an unusual shape, a line where no line was expected, a mound with sharp sides, a cluster of returns that seems too regular to be accidental. At this level, the feature deserves attention, not a name. Low-resolution bathymetry may reveal that something rises from the surrounding seabed, but it cannot explain whether the cause is bedrock, sediment, wreckage, modern equipment, or human construction. The mystery is real because the object is unknown, certainty is not. The next rung is repetition. Researchers return along new survey lines and map the target from several directions. If the form changes or disappears, the original image may have been distorted by noise, navigation error, or the angle of the sonar beam. If the same boundaries remain, the case becomes stronger. The opening anomaly has reached this point. Its ridges survive a second pass, but they are still only measured surfaces. Higher resolution comes next. A vessel or autonomous vehicle moves closer. Multi-beam sonar gives a more precise model of depth. Side scan reveals texture, separate objects, and acoustic shadows. A sub-bottom profiler tests whether the apparent walls rest above the ancient surface or continue downward as layers of natural rock. Then comes direct observation. A camera records the feature continuously, allowing investigators to see how one part connects with the next. Paired lasers provide scale. Photogrammetry can turn overlapping images into a three-dimensional model. Even here, the answer may remain uncertain. Marine growth hides edges. Sediment fills joints. A natural terrace can look more deliberate from one viewpoint than another. The ladder rises through measured relationships. Human construction is rarely proved by one straight line. Stronger evidence appears when walls share dimensions, meet in repeated ways, enclose spaces, contain entrances, or connect with floors, drains, hearths, paths, and activity areas. A settlement is a pattern of related actions, not merely a collection of angles. Artifacts found in place add another rung. A tool resting within an undisturbed floor is more useful than an object recovered from a wide dredging area. Pottery against a wall can help establish use if currents did not carry it there. Cut wood, shaped stone, food remains, and human burials become powerful only when their positions are known. At the highest levels are samples that connect human activity to time. Charcoal sealed beneath a foundation, organic material within construction, or a dated occupation layer directly against a structure may establish when people were present. Several compatible dates are stronger than one spectacular number. This ladder explains why one instrument almost never settles a major claim. Each method sees a different part of the problem. Sonar maps form, cameras show surfaces, cores reveal buried sequences, artifacts show human behavior, dating places events in time. Confidence grows when these independent lines agree. The opening map stands near the lower rungs. It is repeatable and located on an ancient landscape, which makes it worth investigating. No one has yet shown transported blocks, secure artifacts, tool marks, occupation surfaces, or dates tied to construction. Calling it a city now would skip the very steps that could make the discovery meaningful. This is not a method designed to make wonder disappear. It protects wonder from collapsing under weak evidence. Every confirmed submerged settlement once began as an uncertain signal. What separated discovery from illusion was the patient climb upward. That mental leap can happen before evidence is false. It happens because incomplete patterns invite the oldest instincts of recognition and meaning itself. Yet the instruments are not the only source of error. The human observer brings expectations to every image. Once a person sees a street, it becomes difficult to return to an arrangement of ridges. The next danger lies not beneath the sea, but inside the mind that completes its missing walls. The human mind dislikes unfinished shapes. It closes circles that are broken, joins lines separated by darkness, and recognizes faces in stone, clouds, and the pale surface of the moon. It is one of the reasons people can move through a complicated world without examining every detail from the beginning. On a sonar map, however, the same gift can build architecture where the evidence remains incomplete. Two parallel ridges suggest walls. A curved hollow becomes a harbor. Once an observer imagines a settlement, every new feature may be assigned a purpose: a plaza, a gate, a road, a ceremonial platform. Return to the opening anomaly and remove the lines drawn over the image. The supposed buildings become less certain. Other corners depend on shadows created by the chosen direction of digital light. Rotate the map, and a wall becomes the edge of a slope. Change the contrast, and a street seems to vanish into rough ground. The city returns almost instantly. The eye accepts the interpretation because it has been given a pattern to complete. This is often called pattern recognition, but the deeper issue is expectation. A geologist may notice bedding planes and fractures. A filmmaker may notice the shape that will hold an audience. A viewer who has spent years reading about lost civilizations may see confirmation of a much larger story. None of these observers needs to be dishonest. Each can describe the same data sincerely while emphasizing different features. The danger begins when the chosen interpretation is mistaken for the untouched evidence. Natural rock can be surprisingly geometric. Sedimentary layers break along plains. Intersecting joints can produce corners close to right angles. Erosion removes weaker material and leaves terraces, channels, columns, or isolated blocks. Seen underwater, where distance and scale are difficult to judge, these forms may resemble deliberate construction. Human work can also appear irregular. Ancient builders adapted to local stone, repaired structures, reused natural outcrops, and left projects unfinished. Erosion may remove the parts that once made a plan obvious. A genuine site does not need perfect geometry, and a perfect angle does not need a builder. The strongest investigation therefore works against its preferred answer. If researchers suspect architecture, they should ask what natural process could create each feature. If they favor geology, they should identify what evidence would force them to reconsider. A claim becomes more reliable when it survives serious attempts to explain it away. Believers and skeptics can both fail this test. A believer may collect only the images that resemble walls and ignore those that show continuous bedrock. A skeptic may dismiss an anomaly before examining artifacts or buried surfaces. Confidence on either side can arrive long before certainty is earned. Mystery is not protected by choosing the most exciting explanation. It is protected by keeping several explanations alive until evidence removes them. This can feel slower than a dramatic declaration, but it creates a deeper form of suspense. Every new observation has the power to change the balance. There is also an emotional reason people want the ruins to be real. A lost city offers the promise that history is larger than textbooks, that an unknown chapter waits beneath ordinary maps, and that the modern world has forgotten something important. That desire can sharpen attention, but it can also make uncertainty uncomfortable. Imagination helps researchers ask where to look and what might have happened. It becomes dangerous only when it is allowed to finish the investigation. Eventually, the debate must leave the screen. A vehicle must descend toward the target. The apparent wall must be seen at close range, measured, traced, and tested against the surrounding geology. In that moment, some mysteries grow stronger while others dissolve into stone. Yet even direct sight will not be enough. The seabed hides its most important evidence under growth and sediment, and a convincing surface can still tell the wrong story. The decision to return to an anomaly begins long before a robot enters the water. A promising shape may lie beneath shipping traffic, powerful tides, unstable sediment, or water deep enough to turn a simple inspection into an expedition. The vessel first repeats the acoustic survey. New passes overlap the old ones at different angles. If the feature remains, an autonomous underwater vehicle may be sent closer to the bottom. It follows a planned grid without a tether, carrying sonar only tens of meters above the seabed. Targets are then chosen for direct inspection. A remotely operated vehicle descends on a cable, its lights cutting through darkness filled with drifting particles. Marine growth covers edges that looked sharp on the map. The supposed wall appears, disappears behind suspended sediment, and returns as the vehicle moves along its length. Continuous video matters because isolated photographs can be misleading. One frame may show a convincing corner while hiding the fact that the same line continues into natural bedrock. The vehicle follows the feature instead of selecting only its most dramatic surface. Lasers project points a known distance apart, giving scale. If separate blocks are visible, their positions are measured. Investigators look for repeated joints, prepared surfaces, stacking, tool marks, entrances, and connections with floors or paths. They also examine the surrounding geology. Does the feature follow the same rock layer as the ridge behind it? Could erosion have removed softer material and left the apparent structure? Sampling creates a new set of problems. A manipulator arm can lift a shell, stone, or piece of wood, but the value of that object depends on its exact position. An ancient branch lying on the seabed may have traveled from a buried river channel. Even a shaped tool cannot date a wall if no secure connection exists between them. The most important action may be almost invisible on camera. A coring device is pressed into the sediment and returns with a narrow cylinder of layers. One core is taken beside the suspected structure, another inside an apparent enclosure, and others beyond it for comparison. These samples can reveal whether an ancient land surface survives, whether marine mud lies above it, and whether the apparent walls continue downward as natural rock. Reaching the seabed, therefore, does not end uncertainty. Strong currents may prevent stable filming or accurate sampling. The feature that dominated the sonar map may prove to be the least informative part of the site. A thin, dark layer inside a core could carry more evidence than 100 meters of impressive stone. Context is the discipline that holds the expedition together. Every sample needs depth, surrounding sediment, and a record of how it was collected. Data from cameras, sonar, and cores must share the same map. Without that connection, real objects become a collection of facts that cannot answer the central question. This is especially important when claims depend on age. A piece of old wood recovered kilometers from the anomaly cannot date it. A date becomes meaningful only when researchers can say what event it belongs to: a fire on a floor, the construction of a wall, the first marine deposit above a site, or a later object that settled there. The ideal investigation moves slowly from broad detection to narrow proof. Each stage reduces uncertainty while creating new questions. Higher resolution may reveal masonry or show that apparent blocks are continuous bedrock. Video may confirm an alignment, yet cores may find no occupation layer. Samples may establish human presence without proving a city. That result can feel less dramatic than the promise of a lost civilization, but it is how submerged history becomes reliable. The ocean does not surrender a complete answer in one descent. It offers fragments, and each fragment must be placed where it was found. There is already a drowned landscape where this patient method has restored rivers, wetlands, lakes, and hills beneath a modern sea. It once connected Britain to continental Europe. No legendary towers rise from its mud, yet it may be one of the largest lost human environments on Earth. Its name is Doggerland, and its story begins with a blank blue space on the map. On a modern map, the North Sea is a broad field of blue between Britain and continental Europe. Ferries cross it. Fishing vessels work its banks. Storms move across it with little warning. Oil and gas platforms rise above water that seems to have separated these lands for all of recorded memory. Beneath the waves, however, the map is incomplete. During periods of lower sea level, much of this basin was dry. Britain was not an island in the modern sense. Rivers flowed through lowlands that connected eastward and southward. Lakes formed in shallow depressions. Marshes spread across broad valleys. Hills overlooked plains where animals and people could move without crossing open sea. This lost region is known as Doggerland, though no person who lived there used that name. It is a modern label for a landscape that changed repeatedly as climate warmed, ice melted, and water returned. For many years, knowledge of Doggerland came in scattered pieces. Fishing nets and dredging brought up animal bones, worked antler, stone tools, and other objects from the seabed. Each find suggested that dry land had once existed below the fishing grounds, but isolated discoveries could not restore the shape of the country. A different kind of evidence came from surveys conducted for offshore industry. Seismic systems sent sound into layers beneath the seabed, producing vast records of buried geology. The original purpose was not to search for prehistoric settlements, yet within those datasets were the outlines of old river channels, valleys, ridges, and basins hidden beneath later marine sediment. Researchers began assembling these lines into maps. A river appeared, then one of its branches. Depressions became lakes or wetlands. Higher ground separated drainage systems. Gradually, the blank blue space acquired internal geography. The transformation is easy to underestimate. The modern seabed is not simply an ancient plain covered by water. After flooding, currents deposited mud and sand, storms reshaped the bottom, and later channels cut through earlier layers. In many places, the surface on which people once walked lies buried beneath younger marine deposits. This means a vessel can cross an ancient valley without seeing it on ordinary depth maps. The modern bottom may look smooth while seismic profiles reveal a river several meters below. The landscape survives as a hidden shape within sediment. Doggerland was also not one fixed country. At the coldest stages, exposed land extended widely. As sea level rose, its coast moved, plains narrowed, wetlands expanded, and higher areas became islands. A map drawn for one millennium can look very different from a map drawn for the next. That changing geography matters for human life. A river junction attractive during one period may later become an estuary. A hill used as a lookout may become a coastal refuge. Routes between Britain and Europe may narrow, shift, or require boats before disappearing completely. The first great reveal is therefore not a city, it is scale. Beneath a sea often treated as empty space, lies the record of an extensive environment capable of supporting people across many generations. The second reveal is more subtle. Researchers can recover the shape of a country before they recover most of its settlements. Sound can restore the valleys, but the people remain faint. Their camps may be buried, destroyed, or waiting in small preserved pockets that broad industrial surveys were never designed to identify. Doggerland proves that lost worlds do not require legend. Its rivers are not imagined, and its plains are not symbols. They are geological features, mapped beneath modern water. Yet knowing where a river ran does not tell us who stood beside it, what they carried, or how they responded as the sea approached. To bring life back to the map, the investigation must turn from broad terrain to pollen, bone, soil, tools, and the quiet traces of human choice. Such clues restore seasons, journeys, and choices hidden from the maps. To imagine life in Doggerland, it is necessary to resist the picture of an empty plain waiting to be flooded. The landscape was active. Rivers changed course. Wetlands expanded and contracted. Herds moved through open ground. Woodlands thickened as the climate warmed. People read these changes not as distant environmental data, but as the conditions of daily survival. A group approaching a river would notice where the bank remained dry, where animals crossed, and where stone could be found. They might choose a rise above the floodplain, close enough to water, but protected from sudden changes. Fires would be built, tools would be repaired, meat, fish, roots, nuts, and seasonal plants would be prepared, according to knowledge carried through generations. Yet repeated visits could turn a bend in the river into a familiar point within a mental map. A wetland used in spring might be avoided in winter. A grove could mark the route toward another valley. A ridge might provide the first view of distant smoke from another group. Evidence for such lives is scattered and often indirect. Pollen trapped in sediment reveals the plants surrounding ancient channels. Microscopic organisms show whether water was fresh, brackish, or marine. Animal bones indicate the habitats present at different times. Peat and soil layers identify surfaces exposed to air before the sea covered them. Worked stone, bone, and antler recovered from the North Sea demonstrate that humans used the region, even when the exact location of an original camp is unknown. A tool brought up in a fishing net has lost much of its context, but not all of its meaning. Someone selected its material, shaped it, carried it, and left it on land that later disappeared. The difficulty is that Doggerland's geography has returned more clearly than its human settlements. Researchers may trace a buried river for many kilometers, while knowing almost nothing about the families who followed it. They can identify a lake basin before locating the fires once lit along its shore. This reverses the usual order of archaeology. On land, A site may be excavated first, and its wider environment reconstructed around it. Under the North Sea, the ancient environment can be mapped across a vast area, while the sites remain hidden within sediment or lost to erosion. The imbalance creates both frustration and possibility. It means the absence of a mapped village does not equal the absence of people. It also means imagination must remain tied to evidence. The landscape can support a human scene, but it cannot supply names, beliefs, or events that have not survived. Narrow routes between wetlands could guide movement. As the coast shifted, people would have adjusted their camps, fishing grounds, hunting paths, and crossings. For a child born during a period of rising water, the world inherited from older relatives may already have seemed unstable. A place described as inland in a grandparent's memory could become tidal. A familiar route might require a boat. A burial ground or gathering place could stand closer to the sea each year. The change was slow enough in many periods to become part of ordinary life, yet fast enough across generations to reshape memory. People did not need modern measurements to recognize that the water was moving. They would see dead trees at the edge of salt marshes, waves cutting into old ground, and islands forming where hills had once belonged to a larger plain. Doggerland therefore returns not as a frozen map, but as a sequence of shrinking worlds. Its inhabitants were not passive figures waiting for disaster. They adapted, traveled, and chose new places as older ones became difficult to use. But gradual change was not the only force acting on the region. Far to the north, part of the continental slope would fail beneath the sea. The wave that followed may have reached communities already living within a narrowed and fragile landscape. The end of Doggerland is often imagined as a single morning when the sea rushed across a country and erased it. The real transformation was longer, more uneven, and perhaps more unsettling. It unfolded through countless ordinary days during which the shoreline did not return to where older people remembered it. As ice melted, sea level rose. Rivers widened into estuaries, and familiar banks collapsed during storms. Communities could move to higher ground, but higher ground was limited. The places that remained dry became smaller, farther apart, and increasingly surrounded. For one generation, a route might still be crossed on foot during a dry season. For the next, the same journey could require a boat. A hill that once stood inland might become a peninsula, then an island. Freshwater sources near the coast could turn salty. Hunting grounds would change as plants and animals responded to the new environment. This was not a smooth line on a graph. The rate of change varied across centuries and regions. Land itself moved as the weight of ice disappeared. Rivers deposited sediment in one place, while cutting deeply into another. People may have experienced long periods of relative stability, interrupted by rapid local loss. Then came the Storegga event. Off the coast of Norway, an enormous submarine landslide displaced water and generated a tsunami that crossed parts of the North Atlantic and North Sea region. Evidence of its deposits has been found around affected coasts, showing that powerful waves reached areas occupied by people. It is tempting to turn this event into the single death blow that destroyed Doggerland. That makes a clean story, a peaceful country, a sudden wave, and disappearance. The evidence suggests a more complicated picture. By the time of the tsunami, rising seas had already transformed and reduced much of the former land. The wave struck a world that was shrinking, fragmented, and locally vulnerable. Its effects would have varied. Some low coastal areas may have been devastated. Estuaries could have carried water inland. Camps near shore may have been destroyed, while people on higher ground survived. Certain communities might have returned after the waters withdrew. Others may have found that fresh water, food grounds, or routes were permanently changed. The terror of the event does not depend on it erasing an entire country in one day. For those close to the wave, the experience would have been overwhelming. The sea withdrawing, or rising strangely, animals reacting, a distant sound, and then water moving with a force beyond ordinary storms. Yet the larger ending of Doggerland continued through the steady work of sea level. Connections with Britain and continental Europe became water crossings. Eventually, the landscapes that had supported generations survived only as shoals, banks, and buried surfaces. Here, the documentary's central idea changes shape. A sunken civilization does not need walls to represent a profound loss. Doggerland contained roots, seasonal knowledge, familiar rivers, graves, hunting places, and memories tied to ground that no longer exists above water. The disappearance of those relationships may be historically more important than the survival of a single monument. Its reality also strengthens the search for submerged archaeology elsewhere. If an extensive inhabited landscape can lie beneath one of the busiest seas in the world, other continental shelves can preserve their own missing regions. Sonar and seismic data can restore them even when no city appears. At the same time, Doggerland offers a warning. A genuine lost country is not evidence for an unknown Ice Age empire. Human presence, environmental richness, and social memory do not automatically imply monumental urbanism. The most credible mystery may be larger than a city and quieter than a legend. The sea kept the shape of Doggerland while obscuring many of its people. To understand what a confirmed drowned town looks like, the investigation must move south, into clearer and shallower water off Greece. The remains are not older than the last ice age. They do not prove the title's most dramatic possibility. Yet, because their human origin is secure, they provide the comparison every disputed sonar city must face. Beneath the water near Pavlopetri, architecture does not depend on imagination alone. It survives as a connected plan. The water near Pavlopetri is shallow enough for sunlight to reach the seabed. From above, the coast of southern Greece appears calm and ordinary. Beneath the surface, low stone lines cross the sand. They do not rise like towers, and they do not need to. Their meaning comes from the way they connect. Divers following those lines encounter rooms, courtyards, passages, and streets. Foundations meet at corners. Spaces repeat across a recognizable settlement plan. Burial areas lie close to domestic structures. Scattered pottery and other remains belong to a wider archaeological setting, rather than to one isolated shape. This is what makes Pavlopetri different from an underwater formation that merely resembles architecture. Its interpretation does not depend on a single dramatic angle. One wall leads to another. Buildings relate to open areas. Paths continue between groups of rooms. The site can be mapped, measured, revisited, and compared with settlements known on land. Early surveys established the outlines by direct observation. Later projects use sonar, robotic systems, and high-resolution imaging to record the remains more precisely. Thousands of overlapping photographs could be combined into three-dimensional models, allowing researchers to study the plan without relying only on sketches made during short dives. The resulting image is not a fantasy city, reconstructed from a few suggestive stones. It grows from repeated physical relationships. A wall may be low because waves and time removed its upper courses, yet its base still joins another wall in a way consistent with construction. A street may be partly buried, but it continues between buildings. Open areas have boundaries that make sense within the settlement. The strongest evidence is often quiet. Pavlopetri does not present an enormous carved staircase, visible from a great distance. Many remains are broken, covered with sand, or only knee-high. To an untrained eye, a single section may look less impressive than the angular rock at Yonaguni. Archaeologically, however, the modest walls are far more secure because they occur with artifacts, graves, building plans, and repeated human organization. This creates an important contrast. Natural geology can produce spectacular geometry, but it struggles to produce a complete domestic pattern supported by cultural material. Human settlements contain ordinary needs: entrances, movement routes, working spaces, storage, burial, repair, and rebuilding. These connected traces are harder to imitate than one perfect corner. Pavlopetri also reveals the value of scale. A close map can show individual stones and the relationships between them. Surveyors can test whether lines continue, whether apparent rooms have consistent dimensions, and whether features are separate blocks or part of continuous bedrock. Each observation can be placed within the same coordinate system. The settlement was not discovered because one image went viral. Its identity became stronger through years of work, different methods, and the agreement of many small clues. That patient accumulation is what the opening anomaly lacks. Yet Pavlopetri introduces another problem. A city can be unquestionably human-made and still have no connection to the Ice Age. Its buildings belong to a much later period. The water that covers them today does not make them prehistoric in the broadest sense, and their depth does not provide a simple date. This distinction matters because headlines often combine three separate ideas: an ancient settlement, an underwater location, and an extreme age. Pavlopetri confirms the first two. It does not confirm the third. To know when a drowned city existed, researchers must date its occupation and also understand when and why the coast changed. Pottery, building phases, burials, geology, and sea level all contribute different pieces. The moment of construction and the moment of submergence may be separated by centuries. The ruins near Pavlopetri therefore offer both proof and warning. They show that genuine streets can survive beneath the sea. They also show why a visible city cannot be dated by water depth alone. The next mystery lies not in shape, but in time. Every drowned settlement carries at least two clocks. One measures the period when people lived, built, repaired, and buried their dead. The other measures the transformation that placed the site beneath water. Those clocks may point to very different moments. At Pavlopetri, occupation is reconstructed through the material left within and around the buildings. Pottery styles, burial practices, construction phases, and comparisons with better dated sites help establish when the settlement was active. No single fragment carries the entire answer. The chronology emerges because many clues fit the same sequence. The date of submergence requires another investigation. Sea level may rise globally, but local coastlines respond in complicated ways. Land can sink through tectonic movement. Earthquakes can alter elevation. Sediment can compact. Waves can remove protective ground. A harbor can deepen while another coast nearby remains stable. This is why depth is not a clock. A wall 20 meters underwater is not automatically older than a wall 5 meters down. The deeper feature may stand on land that subsided recently. The shallower one may have been drowned for thousands of years on a stable coast. Without local geology, a measurement from the modern surface tells only where the object is now. The mistake becomes especially tempting in Ice Age claims. Researchers know that global sea level stood much lower during glacial periods. A feature found at a certain depth is then placed on a sea level curve, and the time when that depth was exposed is offered as the age of the structure. That calculation can identify when an area may have been dry under simplified conditions. It cannot prove that the feature was built at that moment. Local land movement may alter the comparison. The structure may be natural. Depth provides a question, not a construction date. A stronger chronology begins with events that can be connected. Suppose a foundation cuts into an ancient soil. Charcoal from a sealed hearth lies against the wall. Marine sediment later covers both. Dates from the soil, hearth, and first marine layer can establish a sequence. Land existed, people occupied it, and water arrived afterward. Even then, caution remains. Pottery can be reused or moved. Wood may already have been old when burned. Shells can absorb carbon from environments that affect radiocarbon results. Earthquakes may disturb layers. Several dates from secure positions are needed to reduce the risk that one unusual sample controls the entire story. Pavlopetri's value is that its human identity does not depend on extreme age. Its importance survives ordinary chronology. Streets, buildings, graves, and artifacts reveal a real settlement shaped by coastal change. There is no need to push it back to the end of the Ice Age to make it remarkable. That lesson is easy to overlook in a culture of dramatic headlines. Underwater city sounds older than coastal settlement, even when both refer to the same ruins. Deep water suggests remote time. A dark sonar image feels more ancient than a sunlit wall. The mind connects depth with age, but geology does not promise that relationship. For the opening anomaly, two clocks must therefore be separated from the beginning. First, when was the landscape above water? Second, if any feature was arranged by people, when did that action occur? A model of ancient sea level can help with the first. Only archaeological context can answer the second. The distinction also protects genuine discoveries. If an alignment proves to be a fish trap from a later coastal period, it should not be dismissed because it is not an Ice Age temple. Its true date may reveal an important history of work, navigation, or environmental adaptation. Once the shortcuts of depth and appearance are removed, the investigation returns to the stones themselves. What marks would show that they were transported, prepared, stacked, or used? And what natural processes could create the same visual effect without any builder at all? A stone does not become architecture because one side is straight. Nature produces straight edges with ease, especially where rock is layered, fractured, or exposed to repeated erosion. To identify human work, investigators look for relationships that are difficult to explain as one continuous natural process. At a confirmed settlement, stones may have been transported from another source. Their material differs from the bedrock below. Blocks may rest on prepared foundations, rather than continuing into the ground. Joints break across natural bedding planes, courses repeat, corners enclose spaces, doorways open into paths. Floors carry wear, ash, food remains, broken tools, and objects left during daily activity. No single sign is required at every site. Builders sometimes used rough local stone. Walls can be irregular. Foundations may follow natural ridges. Later erosion can remove upper courses and scatter the parts that once made a plan obvious. The strength of the case comes from several indicators supporting one another. Natural formations can imitate nearly every isolated feature. Sedimentary beds create broad steps. Intersecting fractures form rectangular blocks. Faults produce long, straight faces. Water removes softer layers and leaves platforms, channels, or pillars. Earthquakes separate slabs that appear to have been cut. From above, a network of joints may resemble streets around buildings. The difference often appears when the feature is followed beyond its most impressive view. A natural wall may continue as part of a rock layer across the entire ridge. An apparent staircase may be the exposed edges of tilted beds. A supposed plaza may lack any boundary on the side hidden by shadow. The form looks designed only from one direction. Human sites usually become more coherent under close examination. A doorway leads somewhere. A wall ends for a reason. Rubble collects where an upper section collapsed. Artifacts occur in zones connected with use. Repairs and rebuilding create changes that reflect time rather than geology. Imagine two images placed side by side. The first shows a massive underwater platform with sharp terraces and a face resembling a monument. The second shows several low stone lines partly covered by sand. At first glance, the platform feels more important. It is larger, cleaner, and easier to name. Now add context. The platform is continuous bedrock. Similar fractures appear along the nearby coast. No secure cultural layer has been found. The low walls, by contrast, enclose rooms, connect with streets, contain pottery, and lie beside graves. The less dramatic image becomes the stronger archaeological site. This reversal is central to underwater mystery. Spectacle and proof do not rise together. A feature can be visually perfect and archaeologically weak. Another can be broken, modest, and invisible, while preserving unmistakable evidence of human organization. Tool marks can help, but they also require care. Repeated grooves, cut faces, drill holes, or impact patterns may show working if their form matches known techniques and cannot be explained by natural wear. Random scratches, biological damage, or modern contact can create misleading marks. One line on one stone rarely carries the argument. The same is true of alignment. Stones placed in a row may be a wall, fish trap, boundary, harbor feature, or natural deposit shaped by current. Investigators ask whether the blocks were selected, whether they stand in stable positions, whether the alignment relates to ancient shore conditions, and whether associated material records human activity. The opening anomaly has long ridges and apparent corners, but those features remain at the level of form. The next stages must test material, structure, connection, and context. If the ridges are bedrock, the mystery may shift toward the landscape around them. If separate stones rest upon an ancient surface, a new set of questions begins. The most difficult disputed sites stand between these outcomes. Their geometry is striking, their setting is plausible, and their evidence refuses to settle into one explanation. They invite the eye to see monuments, while giving geology several ways to answer. Off Yonaguni Island, a stepped formation rises through strong currents. Divers have described terraces, passages, platforms, and shapes that seem almost ceremonial. Others see the exposed structure of the island itself, continued beneath the sea. The stone is real. The disagreement concerns the hand that shaped it. The waters around Yonaguni Island can be clear enough to reveal stone at a distance, yet the currents move with a strength that reminds every diver how little control exists beneath the sea. Out of that moving blue rises a formation so angular that the first reaction is often immediate. It looks built. Broad terraces step downward along the rock. Vertical faces meet horizontal surfaces. Narrow passages run between larger masses. The scale deepens the impression. This is not a handful of loose stones resting on sand. The formation is massive, extending across an area large enough to support several architectural interpretations. Photographs taken from favorable angles can appear almost impossible to explain without design. One interpretation proposes that people carved, modified, or used the structure when sea level was lower. Supporters point toward flat surfaces, sharp corners, possible channels, and features that resemble steps. Some have suggested that natural rock provided the basic form, while human hands enlarged terraces or shaped selected areas. Another interpretation begins with the geology of Yonaguni itself. The local sandstone and mudstone occur in layers and contain joints that can break along straight planes. Tectonic activity, weathering, waves, and erosion can expose broad steps and vertical faces. Similar angular rock appears above water on the island, showing that geometry alone does not require builders. These explanations are often presented as opposites, but a third possibility lies between them. A natural formation may have attracted human attention. People could have visited it, climbed it when exposed, marked parts of it, or altered limited surfaces without creating the entire structure. Natural monuments have held cultural meaning in many places without becoming architecture in the strict sense. The problem is deciding which possibility the evidence supports. If the formation were substantially engineered, investigators would expect more than resemblance. Transported blocks, extensive tool marks, cultural deposits, occupation surfaces, repeated construction details, or artifacts securely connected with the stone would strengthen the case. So far, the visual form remains the main source of its fame. This does not make the debate foolish. Seeing the site directly can be persuasive because the human eye encounters continuous scale, depth, and space that photographs cannot fully reproduce. A diver can follow an apparent terrace, turn a corner, and feel as though moving through a designed place. Yet direct experience can also intensify pattern recognition. Strong currents limit the path. Visibility changes. A diver sees sections rather than the entire geology. Once a guide identifies a feature as a staircase or gate, the name shapes everything that follows. The surrounding island provides an important comparison. Above the water, natural cliffs display flat beds, straight fractures, and blocky forms. If similar processes continue below, the underwater terraces become less extraordinary geologically, even while remaining visually remarkable. Official archaeological recognition also matters, though it does not decide nature by authority alone. The formation has not been accepted by Japanese cultural authorities as a confirmed archaeological site. That status reflects the absence of evidence strong enough to establish extensive human construction, not a refusal to consider all unusual underwater features. Yonaguni therefore occupies a precise place on the evidence ladder. Its form is repeatable, visible, and worthy of study. The landscape was exposed during periods of lower sea level. Human contact is possible. Large-scale engineering remains unproved. The most honest conclusion is not that the monument has been solved beyond doubt. It is that three levels of explanation must remain separate. Natural formation with limited human use or modification, and engineered structure. They can all be imagined, but they do not carry equal support. Yonaguni can be photographed, measured, and visited. The next disputed case is harder to see. In the Gulf of Kambat, powerful tides and muddy water make direct observation difficult. There, much of the supposed city first appeared not as stone before a diver, but as patterns inside sonar data. The Gulf of Kambat is not a place where the seabed easily reveals itself. Visibility can fall so low that a diver sees little beyond an outstretched hand. In such water, sound becomes the first guide. Marine surveys recorded submerged channels and geometric-looking patterns beneath the Gulf. Some returns were interpreted as foundations, streets, or parts of a planned settlement. If the structures were human-made and as old as some surrounding material appeared to be, they could predate the better-known urban traditions of the region by thousands of years. Objects recovered during later work added to the excitement. Reports described wood, stone pieces, bones, and fragments, interpreted by some observers as pottery or worked material. One piece of wood produced a very ancient date. In public discussion, the old sample, the sonar shapes, and the drowned river landscape began to merge into one dramatic claim. An ancient city had been found beneath the Gulf. Yet each part of that sentence requires a connection. The sonar patterns must first be shown to represent structures rather than natural seabed forms, survey artifacts, or modern material. The recovered objects must then be shown to come from those structures. Finally, dated samples must belong to an event that reveals when the structures were built or used. The Gulf makes those connections unusually difficult. Powerful currents can move wood, shell, bone, and loose artifacts across the bottom. Rivers can carry material from older deposits and release it far from its original setting. Dredging, or broad grab sampling, may recover genuine ancient objects while destroying the exact relationship between one object and another. A piece of wood can be ancient without belonging to a city. It may have grown beside a river, been buried in an old channel, eroded out, and later settled near a sonar anomaly. The laboratory date can be entirely correct, while the archaeological conclusion remains uncertain. A shaped-looking fragment may be human-worked, naturally broken, or damaged during recovery. Without an undisturbed layer, clear marks, and precise coordinates, its role cannot be confidently tied to the mapped pattern. This does not mean the Gulf contains nothing important. Submerged river systems demonstrate that the environment was once different. Dry land, fresh water, and changing coastlines created places where people could have lived or traveled. Ancient material in the region may reveal human activity across landscapes now drowned. The larger claim, however, is urban planning. Streets and buildings require repeated architectural relationships. A city requires more than scattered objects. It needs secure walls, activity areas, cultural layers, and dates connected with those features. Turbid water and disturbed sediment make that evidence difficult to obtain, but difficulty cannot be replaced by assumption. The most revealing contrast is between headline and method. A headline asks whether the oldest city on Earth has been discovered. Archaeology asks where each sample was found, what layer held it, whether currents moved it, what the sonar processing did to the image, and whether another survey produces the same plan. Those slower questions can sound less exciting, yet they protect the possibility of a real discovery. If future work identifies an intact occupation surface beneath the Gulf, its meaning will depend on records detailed enough to survive doubt. Without that discipline, even remarkable material remains vulnerable to every alternative explanation. The Gulf of Khumbat therefore stands neither as a confirmed Ice Age city nor as an empty fantasy. It is a submerged landscape containing intriguing signals and reported ancient material, but the association between them remains the central problem. This association problem appears again and again in underwater mysteries. When they occur in the same area, the mind wants them to belong to one story. But three ancient things can be genuine and still be unrelated. The next step is to separate them on an imaginary table and ask what evidence would be needed to place them together. Place three pieces of evidence on a table. The first is a map of an ancient river valley now buried beneath the sea. The second is a geometric stone feature recorded by sonar. The third is a piece of wood dated to a remote period. Each item may be genuine. The mistake begins when their separate ages and locations are compressed into one sentence. The wood dates the city. For that sentence to be valid, the wood must belong to an event connected with the structure. Its position must be recorded well enough to show that currents, rivers, dredging, animals, or later human activity did not place it there. Without that connection, several other stories remain possible. The wood may have grown in the valley long before the stone feature existed. It may have been eroded from an older layer and carried across the seabed. The stone may be natural bedrock, millions of years older than both the wood and any human occupation. A later object could also settle upon an ancient surface, making the relationship younger than the landscape below. This is the association problem. Most disputed underwater claims do not require anyone to invent all the evidence. Real data can be assembled into a false certainty when the links between pieces are assumed rather than demonstrated. The same problem appears with dates from shell, bone, and charcoal. A shell attached to a stone can show that the surface was underwater by the time the animal grew. It does not reveal when the stone was placed. Charcoal nearby may record a fire, but not necessarily a fire made by builders. Bone can prove the presence of an animal or person, yet currents may have moved it after burial. Even the age of a drowned landscape must be handled carefully. A valley may have been dry during the Ice Age and flooded later. That fact creates an opportunity for human occupation, not proof of it. A rock formation standing within the valley may predate the valley's human use. If people modified the rock, the relevant date is the modification, not the geological birth of the stone. Popular storytelling often hides these distinctions because separate facts feel stronger when combined. Ancient wood found near geometric ruins is more exciting than old material recovered from a disturbed marine area containing uncertain sonar features. The shorter phrase creates an image the evidence has not yet earned. Scientific caution can sound evasive when listeners want a verdict. Yet the demand for association protects extraordinary discoveries from easy collapse. A securely dated beam inside a constructed wall would be far more powerful than dozens of ancient objects collected without context. One modest sample in the right place can outweigh a warehouse of impressive fragments. For Yonaguni, the question is whether cultural material and signs of working can be tied to specific surfaces. For the Gulf of Kambat, the question is whether recovered material can be connected to stable structures and undisturbed layers. For the opening anomaly, the same rule applies before any date is announced. This also explains why honest disagreement can continue for years. One side emphasizes the reality of the shapes and the ancient environment. Another emphasizes the missing link between shape, object, and time. They disagree about whether the facts form one event. The path forward is clear, but demanding. Researchers must recover samples from controlled positions, map the surrounding layers, test natural explanations, and repeat the chronology across several points. The goal is a sequence in which each event rests above or below another. Natural ground, human activity, construction, abandonment, flooding, and marine burial. Only then can age move from object to site. To date a megalithic city older than the end of the Ice Age, investigators would need more than an old number. They would need evidence showing that people arranged stone at that time, occupied the place, and left a pattern broad enough to justify the word city. That challenge leads away from spectacular sonar images and into the quieter world of laboratories and sediment cores. Stone itself carries no construction date. The age must be found in what lies beneath it, against it, within it, and above it. A stone block on the seabed can be measured in seconds. Its length, width, depth, and position can be recorded with remarkable precision. Its age is harder because stone carries many ages at once. A geologist may determine when the rock itself formed. That date could reach back millions of years, long before humans existed. An archaeologist asks a different question. When was the stone quarried, moved, shaped, placed, used, repaired, abandoned, buried, or submerged? Those events do not leave a simple clock inside the rock. Their dates must be found in relationships around it. Charcoal beneath a foundation may belong to activity that occurred before or during construction. Organic material trapped within mortar can be connected with building. Wood used as a beam may provide a direct sample if it remained in place. Sediment sealing a wall can show that construction is older than the layer above. Each sample answers only the question allowed by its position. A shell growing on the surface of a submerged block shows that the block was underwater when the animal lived. It does not reveal when the block was built. A piece of charcoal resting nearby may date a fire. but not necessarily a fire connected with construction. Ancient soil beneath the stone can show that dry ground existed, yet the stone may have been placed much later. Even an accurate laboratory result can therefore support the wrong story. Imagine a wooden beam reused from an older structure. Radiocarbon dating may correctly reveal the age of the tree, while the wall containing it was built centuries afterward. This is sometimes called the old wood problem, but the principle extends beyond wood. Materials can survive, move, and be reused. Marine environments introduce further complications. Shells and organisms obtain carbon from water that may contain older sources, affecting apparent ages if corrections are not carefully made. Currents can carry organic material into cracks. Burrowing animals can mix layers. Roots from a later period may penetrate older ground before flooding. A single clean number can hide a complicated history. Charcoal beneath a foundation provides one limit. Material within a floor provides another. Marine organisms attached after flooding offer a later boundary. Sediment above the site records burial. When those dates agree in the correct order, confidence grows. This is why one spectacular result should rarely control an extraordinary claim. A date becomes strong when it fits archaeology, geology, and stratigraphy rather than standing alone. Repetition matters, but simple repetition is not enough. 10 pieces of driftwood from one disturbed layer may repeat the age of an old forest without dating any nearby wall. The opening anomaly would require a chronology tied to action. If investigators found charcoal sealed beneath separate stones resting on an ancient surface, they could begin asking when placement occurred. If the supposed walls continued downward as natural bedrock, no construction date would exist. The correct age would belong to the geological formation, not to an imagined city. Yonaguni presents the same challenge. The stone's geological age does not establish human modification. A very old surface can be altered in a much later period. The relevant evidence would need to date the alteration or cultural activity connected with it. In the Gulf of Kumbat, ancient wood cannot transfer its age to a sonar pattern through proximity alone. The sample must belong to the structure, and the structure must first be shown to be human-made. These distinctions are less dramatic than announcing the world's oldest city, but they decide whether such an announcement survives. Archaeology is not searching for the oldest object in the area. It is reconstructing the order of events. A single date can transform a headline overnight. A sequence of quieter dates can transform history. To build that sequence underwater, researchers often depend on an object that looks almost meaningless when lifted onto the deck, a narrow cylinder of mud. When a sediment core rises from the seabed, it rarely resembles treasure. It is a tube filled with mud, sand, shell, dark organic bands, and colors that shift by only a few shades. Yet those layers can preserve the order of events more faithfully than an exposed monument. The lowest part of a core may contain terrestrial soil formed when the area faced the air. Roots, pollen, plant fragments, and chemical traces reveal the environment above it. A freshwater layer may show that a lake or river occupied the site. Higher in the sequence, brackish organisms can record the first arrival of tides. Marine mud marks a later world in which the old landscape lay beneath the sea. Now imagine a core taken through a suspected settlement. At the bottom lies natural ground. Above it rests a thin occupation layer containing charcoal, stone flakes, food remains, and compacted soil. Foundation stones cut into that surface. Sediment later gathers inside the structure. A flood or storm leaves a distinct band. Finally, marine deposits cover everything. If several cores reproduce that order, the site begins to acquire a history. Samples from beneath the foundations establish that construction came later. Material within the occupation layer connects people with the surface. The first marine layer places a boundary on submergence. Dates from different points can be compared, rather than trusted in isolation. The sequence can also expose a false city. A core beside an apparent wall may show that the stone continues downward without interruption, forming part of the same bedrock layer as the surrounding ridge. No ancient floor lies against it. No cultural debris appears. Marine sediment has accumulated naturally along the rock. The sonar image may remain beautiful. Its corners may still look architectural from above, yet the core removes the need for builders. What seemed like a wall becomes the exposed edge of geology, and the mystery moves elsewhere. Mud is persuasive because it records position. A charcoal fragment in a sealed band has a different meaning from charcoal loose on the seabed. Pollen beneath a wall belongs to an earlier landscape. Shell above it belongs to a later marine phase. The vertical order provides the grammar that turns separate objects into a sentence. Cores are not perfect. A device can compress soft layers. Burrowing animals mix old and young material. Storms cut into earlier deposits and replace them with later sediment. A sample taken a few meters away may miss a narrow occupation surface entirely. Researchers therefore take many cores and compare them with sonar, geology, and direct observation. The opening anomaly would require this kind of patient grid. Cores inside the apparent enclosures could test for flaws and trap deposits. Samples across the long ridges could reveal whether they are built above the surface or rooted within natural layers. Cores beyond the feature would provide a background sequence for the wider landscape. A single core can produce an exciting date, but a pattern of cores can establish a site. If charcoal, artifacts, and ancient soil repeatedly occur within bounded spaces, the case for human activity grows. If every apparent wall proves continuous with bedrock, the architectural interpretation weakens. This method also separates occupation from flooding. People may have used the landscape for centuries before water arrived. A storm layer could mark sudden local destruction, while later, marine mud records gradual deepening. The site can hold several endings rather than one catastrophic moment. The quiet power of sediment changes the hierarchy of evidence. The massive stone attracts cameras, but the narrow core may decide the argument. One records appearance, the other can record sequence. Even a perfect sequence, however, would not automatically prove a city. The word city requires evidence of scale, organization, and sustained life beyond the age of the samples. The investigation must therefore ask not only when people were present, but what kind of place they created. The word city enters underwater stories easily because it gives scattered shapes a familiar scale. Yet a city is not simply a large place with stones. Definitions vary across regions and periods, but urban life usually leaves several kinds of organization. People remain long enough to build, repair, discard, and rebuild. Space is divided for homes, work, storage, gathering, movement, water, burial, or defense. Activities create concentrated debris. Structures connect with roots. The settlement also relates to smaller places around it through trade, food, labor, kinship, or authority. None of these features must resemble a modern city. Early urban communities could be low, crowded, irregular, and built from materials that rarely survive. Writing, metal, kings, and monumental temples are not required in every definition. What matters is sustained complexity, visible through connected evidence. Now imagine a late glacial site discovered beneath marine sediment. It contains hearths, post holes, stone foundations, burials, tools, and carefully arranged blocks. The dates are secure. The evidence would be extraordinary. It could transform understanding of coastal settlement, communal work, ritual behavior, and adaptation near the end of the Ice Age. But should it be called a city? If the features belong to several small dwellings used seasonally, the word may hide more than it reveals. If the stones form a fish trap, their construction may show cooperation and detailed knowledge of tides without implying urban government. If the place served as a gathering ground used by dispersed groups, its social importance could be enormous, even without permanent population. Monumental behavior also does not guarantee a state or metropolis. Communities can organize demanding projects through kinship, ritual obligation, seasonal cooperation, or shared need. Large stones may mark a place that mattered deeply, while surrounding life remained mobile. The opposite is equally important. A society can possess sophisticated knowledge without building monumental stone. Boats made from wood, hide, fiber, or reeds may vanish. Navigation exists in memory rather than architecture. Fishing grounds, weather patterns, and distant routes can be mastered without leaving towers. Seasonal networks may connect large populations through gatherings that occupy only part of the year. Modern categories can therefore make early coastal societies seem simpler than they were. Archaeology often measures what survives, and stone survives better than skill. A coastline community may leave little durable architecture while carrying knowledge essential to movement, exchange, and survival. This reframes the search beneath the sea. The most important discovery may not be an Ice Age metropolis with avenues and temples. It may be evidence that coastal groups formed larger networks, engineered shorelines, returned to shared centers, or organized work on a scale not visible in the surviving inland record. Such a conclusion would still challenge familiar history. It would suggest that the social world of prehistoric coasts was richer than the land evidence alone implies. It might explain the rapid spread of ideas, materials, or people along routes now drowned. The scale of the claim must match the scale of the evidence. One alignment can support human placement. Several structures with floors and artifacts can support settlement. Repeated neighborhoods, infrastructure, specialized activity, and regional connections begin to support urbanism. This discipline does not reduce every discovery to a campsite. It allows each site to become important for what it actually was. Calling a fish trap a failed city would miss the intelligence of its design. Calling a seasonal gathering place an empire would bury its real social meaning under a dramatic label. The opening anomaly may eventually reveal no architecture, limited modification, a small constructed feature, a settlement, or something larger. Each outcome requires different evidence. The word city belongs near the end of the investigation, not at the beginning. And this leads to a broader possibility. If attractive coastal zones were submerged across the world, then conventional archaeology may be working with a record missing many of the places where people met, traveled, exchanged, and experimented. The sea may not conceal one forgotten civilization. It may conceal a lost dimension of human adaptation. To understand how large that absence could be, the investigation must look at the maps archaeologists use and ask a simple question: what happens when the ancient shoreline is drawn back onto them? Open a map of early archaeological sites, and certain places appear crowded with evidence. Caves, rock shelters, river terraces, and inland valleys carry dots representing tools, hearths, bones, burials, and art. Along many continental edges, the pattern becomes thinner. The first explanation may seem cultural. Perhaps people favored the interior. Perhaps coastlines were used only occasionally. Perhaps marine resources became important much later. Yet another possibility is built into the map itself. The coast being examined is the wrong coast. Draw the shoreline as it existed during lower sea level, and broad areas of missing land return. The empty edge moves outward. River systems continue across shelves. Valleys connect with plains. Islands join. Many dots that seemed inland now sit closer to ancient estuaries, lakes, or coastlines. This does not prove that every submerged shelf was heavily occupied. It reveals a bias in what can be found. Sites remaining on dry land are easier to discover, excavate, revisit, and compare. Drowned sites require vessels, remote sensing, divers or robots, specialized permits, favorable weather, and large budgets. Their absence from the record may reflect the difficulty of searching rather than the choices of ancient people. Preservation adds another filter. Rising water destroys some sites before covering them. Others are sealed beneath sediment. A map showing known sites therefore combines human behavior with geological survival and research effort. It is not a neutral picture of where people lived. The effect can reach far beyond coastal archaeology. If shoreline camps are missing, researchers may underestimate fishing, boating, shell gathering, and movement along the sea. If submerged crossings are ignored, migration routes can appear longer or more dangerous than they were. Exchange between regions may seem rare because the connecting places lie underwater. The inland record can also exaggerate the importance of caves. Caves preserve material well and remain visible. Open-air coastal camps often survive poorly even before flooding. A history built mainly from caves may describe what preservation selected, not the full range of human life. This is the inland bias, not a deliberate refusal to study the coast, but a structural imbalance created by modern geography. Archaeology began and developed where people could walk, dig, and return. The sea requires a different set of tools, and those tools have only recently begun mapping areas at useful resolution. Even now, much of the continental shelf is known more for navigation, industry, or geology than for archaeology. Broad bathymetric maps may show major terrain while missing small features. Industrial seismic data can reveal buried valleys, but their survey spacing may be too coarse to locate camps. An ancient surface can exist between lines that were collected for another purpose. The first reveal is therefore simple but enormous. For much of human existence, the present shoreline did not define the edge of the habitable world. Treating it as permanent removes large areas from the search before evidence is considered. The second reveal concerns scale. The ocean may not hide one central civilization waiting to explain every mystery. It almost certainly hides countless ordinary places: camps, crossings, working grounds, fish traps, burials, and routes. Together, those places could alter understanding of population, movement, food, technology, and social connection. A small coastal site dated securely can change the timing of migration. A preserved boat landing can reveal water travel. A sequence of shell processing areas can show repeated seasonal use. A burial beside a drowned river can restore a human presence to an empty map. The search should therefore begin where people were likely to choose, not only where sonar displays dramatic geometry. Ancient freshwater, shelter, resources, and preserved ground matter more than visual spectacle. Some of the best targets may lie beneath smooth mud at buried river mouths, invisible to an ordinary camera and barely expressed on the modern seabed. To find them, researchers must predict human choices across a landscape that no longer exists. Searching an entire continental shelf at archaeological detail would be impossible. The area is too large, the cost too high, and the seabed too varied. Researchers therefore begin with a simpler question: where would people have chosen to stop? Ancient rivers, springs, and lakes would attract humans and animals. Sheltered ground offers protection from wind and waves. These features can be reconstructed even when the bottom looks empty. Bathymetry reveals broad hills and valleys. Sub-bottom profiles trace buried channels beneath sediment. Cores identify ancient soil, peat, freshwater deposits, and the transition to marine conditions. Models estimate where erosion removed old surfaces and where mud may have protected them. Evidence from surviving land sites helps refine the search. If people in a region repeatedly chose river junctions or sheltered terraces, similar locations can be identified offshore. Local and indigenous knowledge can also matter. Oral histories may preserve memories of changing coasts, drowned places, ancestral routes, or culturally important seascapes. Such knowledge should not be forced into literal maps without care, but it can guide questions that remote sensing alone would never ask. The resulting map today does not mark cities. It marks probability. A third may have been scoured by waves so completely that little evidence is likely to remain. This leads to a surprising reversal. The most visually impressive seabed is not always the best archaeological target. Exposed rock produces dramatic sonar shadows, but it may have lost every fragile trace of occupation. A smooth plain of mud can look lifeless while sealing an ancient surface below. Researchers often rank targets by combining human attraction with preservation. A freshwater junction on stable ground is promising. If that surface was buried quickly and later protected from strong currents, its value rises. If the same place lies within an area heavily disturbed by dredging, trawling, or construction, the chance of intact context falls. Survey then proceeds from broad to narrow. Existing industrial data reveal major buried landscapes. A new multi-beam survey maps the bottom. Sub-bottom lines identify preserved layers. Cores test the age and environment. Only after these stages do divers or robots focus on small areas where human traces may survive. The method lacks the instant drama of discovering a rectangular shape. Its suspense builds differently. Each layer of evidence reduces a vast ocean to a smaller field, then to a buried terrace, then to a band of ancient soil. The target becomes more important as it becomes less visible. Suppose a core from such a terrace contains charcoal, stone flakes, and seeds within a soil that formed before flooding. A second core finds the same layer nearby. High-resolution mapping reveals a shallow depression and several aligned stones above it. The discovery begins not as a city, but as a place where human activity can be tested in context. That is the necessary beginning of any claim capable of changing history. Architecture, if present, must emerge from the preserved landscape rather than being imposed upon it. Predictive archaeology also protects limited resources. Ships and robotic systems can spend days examining one target. Weather may close the survey window. Every descent has a cost. Choosing locations through evidence increases the chance that those hours answer meaningful questions. The method cannot guarantee a settlement, and it will sometimes miss places used for reasons no model can predict. Sacred locations, sudden events, and individual choices do not always follow practical logic. Models guide attention. They do not replace discovery. Even when a site is found, another problem remains. Erosion may have removed its edges, scattered its artifacts, or erased the evidence needed to measure its original size. A small surviving patch might be the last piece of something much larger. The next question is therefore uncomfortable. Could an organized coastal society disappear so completely that only a few uncertain traces remain? Or should a civilization leave evidence beyond the seabed itself? If an Ice Age civilization built cities along vanished coasts, the sea would not be the only place to search for it. A society capable of sustained urban construction would leave a wider footprint. Quarries, workshops, tools, transport routes, food production, human remains, waste, trade goods, and related settlements on ground that remained dry. The larger the proposed civilization, the more kinds of evidence it should produce. An entire urban network should create traces across regions, materials, and generations. Paths would connect the site with water, raw materials, and surrounding communities. Objects and ideas would travel beyond the coast. Some evidence should appear in caves, uplands, river valleys, or later traditions that survived flooding. The absence of such a network does not prove that no unexpected society existed. Later, people reuse useful places and stones. A civilization known mainly through wood, fiber, earth, hide, and oral knowledge could leave far less than a stone-building culture. This opens a second possibility, less cinematic but perhaps more plausible. Small maritime societies may have possessed skills and organization underestimated by surviving evidence. Boats can disappear completely. Nets, ropes, baskets, sails, and wooden structures rarely endure. Knowledge of currents, stars, weather, fish movements, distant islands, and seasonal resources may leave no direct object at all. Such communities could connect broad territories without becoming urban states. They might gather periodically at certain coasts, build communal traps or markers, exchange stone and stories, arrange marriages, perform ceremonies, and then disperse. Their social world could be complex, even if their settlements were temporary. Rising seas would damage this record severely. The locations used most often near estuaries and sheltered bays might be the first to erode. Storms could scatter light structures. Later sediment might preserve only small pockets. On surviving land, the same people could leave camps that appear isolated because the coastal centers linking them are gone. This possibility deserves serious attention because complexity is not identical to monumentality. Human intelligence does not begin when stone walls become large enough for sonar to detect. Navigation, cooperation, environmental memory, and social networks can be sophisticated without producing a city. Yet preservation limits cannot explain every missing trace without limit. When a claim expands into a global advanced empire, the expected footprint expands as well. Specialized technology should leave tools and production debris. Large populations should leave biological and environmental effects. Wide trade should distribute distinctive materials. Repeated architecture should appear in more than one uncertain location. The door therefore remains open, but not equally wide for every idea. Undiscovered coastal communities are almost certain. Unexpected engineering and large gathering places are plausible. A worldwide Ice Age urban civilization, leaving no secure network on surviving land, requires much stronger evidence than geometric sonar alone. This balanced conclusion may disappoint anyone seeking a single hidden culture behind every ancient mystery. It offers something richer instead. Human prehistory may contain many regional experiments in coastal life, each shaped by local seas, rivers, resources, and traditions. Their disappearance would create gaps that later generations could mistake for sudden beginnings. A fish trap can reveal collective planning. A landing place can reveal repeated water travel. A buried workshop can show specialized skill. Several linked sites can reveal a network. Each discovery adds complexity through evidence rather than through labels. For the opening anomaly, the scale test will remain essential. If investigators find one small arranged feature, they should search the surrounding landscape for activity areas and related sites. If they claim a city, they must locate the patterns of sustained settlement. If they claim a civilization, the search must extend beyond the coordinates. The future of this investigation will depend on machines capable of covering more ground than divers can see. Autonomous vehicles now fly through darkness near the seabed, collecting maps at a resolution earlier explorers could not imagine. Algorithms can examine archives containing millions of acoustic returns. The next anomaly may already have been recorded. It may be waiting unnoticed inside data gathered for a pipeline, a wind farm, a naval survey, or a geological study. But finding more shapes will not remove the need for the scale test. It will only give the test more places to begin. An autonomous underwater vehicle does not descend like a diver. It slips beneath the surface without an air hose or tether, following instructions written before the sea closes above it. Once beyond sight, it moves through darkness, using navigation sensors, depth readings, and planned survey lines. Mounted along its body are instruments designed to see with sound. Multi-beam sonar maps the shape of the bottom. Side-scan sonar records texture and objects to either side. Cameras wait for moments when water clarity and distance allow useful images. The advantage is closeness. A sonar system on a surface vessel may be hundreds or thousands of meters above the target. An autonomous vehicle can fly tens of meters above the seabed, producing sharper detail. It can follow terrain too deep for diving and work where strong currents, cold or distance, make human exploration dangerous. Its path appears simple on a map, parallel lines crossing a rectangle. In reality, the vehicle must maintain height above slopes, avoid obstacles, correct for currents, and return with enough power to be recovered. The full landscape remains hidden until data are downloaded. A remotely operated vehicle serves a different purpose. Connected to the ship by a cable, it carries live video and can respond to instructions. Pilots turn toward a wall, lower a sampling arm, or follow an alignment beyond the planned route. The tether limits range and can be difficult in current, but human judgment reaches the seabed in real time. They can carry sonar across wide areas for long periods with smaller crews. Together, these machines expand the portion of ocean that can be examined while reducing the need to place people in dangerous water. Their growing use changes the nature of discovery. In older exploration stories, the decisive moment belongs to the person who first sees an object. The machine passes over a feature during a routine mission. Months later, someone reviewing the data notices a pattern that no one recognized at sea. An archive can therefore contain unseen landscapes. Surveys collected for cables, energy projects, navigation, fisheries, defense, or geology may cross ancient river valleys and archaeological sites without being designed to find them. The data already exist, but the question has not yet been asked. Higher resolution creates its own reversals. A low-detail map may show a perfect rectangle. The closer survey reveals that one side is missing, another follows a natural fracture, and the center contains irregular rock. A mystery can dissolve as the image improves. A broad anomaly that seemed unremarkable may separate into repeated walls, individual blocks, entrances, or artifacts. New detail can turn background noise into a target worthy of direct inspection. This uncertainty gives each mission a quiet suspense. The vehicle returns to the surface, carrying no golden object and no visible answer. Its most important cargo is a memory of sound stored on drives. Only after processing do ridges rise, channels deepen, and small shadows appear beside objects on the bottom. The opening anomaly would benefit from this close mapping. An autonomous vehicle could test whether the long ridges remain straight at finer scale, whether blocks are separate, and whether apparent enclosures repeat. It could also identify safe routes for a tethered robot and precise locations for cores. Yet machines do not escape interpretation. Software joins survey lines. Artificial lighting creates depth. A better instrument reduces uncertainty. It does not remove the human mind from the process. The amount of data is also becoming too large for human eyes to examine every return. Thousands of kilometers of seabed can be mapped during programs. Each survey contains patterns, anomalies, and noise. To search this expanding archive, researchers are teaching algorithms to rank unusual targets. The promise is enormous. A machine may find shapes overlooked for years. The danger is equally clear. An algorithm can learn the same expectations that cause people to see cities in stone. A sonar archive can contain millions of decisions waiting to be made. Human reviewers can study only a fraction of the material, so automated systems are increasingly asked to narrow the search. Show it known shipwrecks, pipelines, boulders, anchor scars, and natural channels, and it learns patterns that help rank new targets. It can compare shape, texture, shadow, size, and surrounding terrain across more images than a team could inspect manually. For underwater archaeology, the promise is obvious. Decades of mapping collected for industry, defense, and science may hold features no one noticed. A system could search broad regions for buried river valleys, preserved terraces, unusual alignments, or objects with the acoustic signature of wreckage. Human experts would then examine the highest-ranked results. But the machine does not understand ruins. It recognizes similarity within the examples and rules provided. If most training data contain modern shipwrecks, the system may become skilled at finding metal hulls while ignoring prehistoric sites with no comparable shape. If rectangular geometry is treated as evidence of architecture, natural fractures may be flagged again and again. The problem is not artificial intelligence becoming imaginative. It is artificial intelligence scaling human assumptions. A mistaken expectation applied by one observer affects one map. The same expectation built into an automated search can affect an ocean of data. Confidence scores can deepen the illusion. A result labeled 95% structure may sound like a scientific verdict. In reality, it may mean that the target resembles the patterns the model was taught to associate with structures. If the training examples were incomplete or biased, the number measures consistency with that bias. Ground truth remains essential. High-ranked targets must be mapped again, viewed directly when possible, sampled, and compared with geology. The algorithm can decide where attention goes. It cannot decide that human hands built a city. There are also practical sources of confusion. Different sonar settings alter texture. Fishing gear, cables, debris, biological reefs, and modern construction can resemble archaeological features. A model trained in one seabed environment may perform poorly in another. The strongest systems may therefore search for landscapes before monuments. Ancient channels, freshwater basins, stable surfaces, and zones of rapid burial can be identified through patterns broader than a single wall. These targets guide researchers toward places where human evidence has a chance of surviving in context. Imagine an algorithm examining an old industrial dataset from the continental shelf. It does not announce a city. It identifies a buried river terrace with unusual preservation, several repeated high returns, and a gap in the geological explanation. That result can be combined with sea-level models, nearby land archaeology, and new cores. This approach reduces the temptation to treat geometry as the entire discovery. A wall-shaped return becomes one clue within a landscape rather than the center of a legend. The machine assists by finding relationships too numerous for manual review. Researchers must record which data trained the model, what features it ranks, where it fails, and how results change under different settings. Without that information, an algorithm can become another dark box producing images that look authoritative. The opening anomaly could be tested by training systems on local geology and known human-made features, rather than on generic rectangles. If the pattern remains unusual after those comparisons, its priority rises. If similar forms appear across natural outcrops nearby, the mystery narrows. Artificial intelligence will accelerate discovery, but it will also accelerate error. More targets will be found, shared, and interpreted before fieldwork reaches them. The old discipline of context becomes more important, not less. The strongest future expedition will combine machine scale with human caution. It will search not only for stone, but for ancient soil, environmental change, biological traces, and the sequence of burial. The question will move from, does this look like a city, to what history can this landscape actually support? A mission capable of testing the opening anomaly would begin with restraint. Before a ship leaves port, the team would gather every existing survey, geological report, sediment record, sea level model, and archaeological find from the region. Old data might reveal that the apparent city lies beside a buried channel, across a known fault, or within an area disturbed by modern work. The first days at sea would be devoted to mapping rather than excavation. A surface vessel would cross the coordinates along overlapping lines, collecting multi-beam depth data and side-scan imagery from several directions. Survey settings would be recorded so that later researchers could reproduce the processing instead of seeing only the final shaded image. Sub-bottom profiles would test the most important division. Do the long ridges rest upon an ancient surface, or do they continue downward as part of the natural bedrock? A wall built by people should relate to the ground differently from a geological layer, even if erosion has blurred that relationship. An autonomous vehicle would then fly closer. Its finer map would locate separate blocks, small depressions, possible entrances, and zones where sediment has gathered. The data would also identify hazards and guide a remotely operated vehicle toward targets chosen before anyone sees them on camera. That order matters. If pilots simply follow the most impressive shapes, the expedition may collect beautiful footage while ignoring less visible evidence. A planned route forces the robot to examine natural comparison areas, apparent structures, and the spaces between them. Continuous video would be recorded with scale lasers and precise positioning. The vehicle would trace each ridge to its end. It would inspect joints, bedding, surfaces, and nearby outcrops. Samples would be taken only when their position and surrounding layer could be documented. Cores would form a grid across the site. Some would pass through apparent enclosures, others would lie against the ridges, inside buried channels, and beyond the anomaly. Laboratories would examine pollen, shell, charcoal, plant remains, microfossils, soil chemistry, and possible environmental DNA. Together, these traces could reconstruct whether the area was dry, wetland, freshwater, tidal, or fully marine at different times. Archaeologists would search for floors, hearths, post holes, tool scatters, and repeated spatial organization. Geologists working independently would model how local rock fractures, erodes, and appears under sonar. The two groups would not be asked to defend opposing camps. They would be asked to produce explanations that make testable predictions. If geology predicts similar ridges nearby, new lines would look for them. If construction is suspected, cores and cameras would search for transported stone, prepared foundations, cultural layers, and associated artifacts. Every result would be added to the same coordinate system. The raw data would be preserved. Processing choices would be published. Dates would include sample position, material, laboratory method, and uncertainty. Outside researchers would need enough information to challenge the interpretation without repeating the entire expedition. This standard may seem excessive until the cost of a false conclusion is considered. A viral image can circle the world in hours. A claim of the oldest city can become permanent in public memory, even after later evidence weakens it. Careful records allow the discovery to mature instead of hardening into legend. The expedition would also face a race against damage. Trawling can disturb surfaces, anchors can break walls. Dredging, pipelines, wind development, mineral extraction, looting, and storms can destroy a site before its value is understood. A place does not need to be fully proven before temporary protection becomes reasonable. Years may pass between the first survey and a reliable conclusion. Weather interrupts work, samples require analysis, conflicting dates demand new cores. Funding ends, equipment fails. The ocean does not adjust its schedule to human curiosity, yet patience is part of the evidence. A conclusion that survives repeated seasons, independent teams, and improved instruments is stronger than one born from a single expedition. At last, the investigation can return to the opening map. The outlines will no longer stand alone. High-resolution sonar, direct video, geology, cores, artifacts, and dates will surround them. One buried line beneath the apparent walls may decide whether the city rises from the data or disappears into the natural landscape. The vessel returns today to the coordinates under a sky much like the one in the opening. The sea offers no sign that anything unusual lies below. On the first map, the ridges still resemble walls, the raised surface still suggests a platform, and the empty spaces still invite the mind to imagine rooms. This time, however, every image arrives with a question attached. The new multi-beam survey confirms that the long ridges are real. They occupy the positions recorded during the earlier passes, and several remain strikingly straight across part of their length. The anomaly was not created by one moment of interference or a simple navigation error. Higher resolution changes the plan. Some boundaries that appeared continuous break into separate rises. Several corners soften. The platform becomes an uneven terrace with a steeper edge on one side, yet two short alignments remain difficult to explain as parts of the wider pattern. Side scan imagery reveals different textures. The largest ridges cast broad shadows and share the same acoustic character as exposed rock nearby. Smaller objects at the edge of the terrace return brighter signals and appear separate from the surface beneath them. Their positions are regular enough to deserve attention, though not regular enough to declare construction. Then the sub-bottom profiles arrive. Beneath most of the supposed walls, the signal continues downward through sediment and joins a buried geological layer. What looked like a foundation is the upper edge of rock, extending below the ancient ground. The main city plan loses its strongest claim. This is the moment when an exaggerated documentary would turn away, or pretend the data say something else. But the disappearance of the city does not make the site empty. Cores taken across the terrace contain marine mud above an older surface formed on land. Pollen and freshwater indicators show that the area once lay beside a channel in a cooler environment. A band of terrestrial soil survives beneath later sediment. The location was not merely exposed rock. It was part of a real vanished landscape. The dates place that surface within a period when people could have moved through the region. No direct sign of occupation has yet been found in the first cores, but preservation is better than researchers expected. The old ground did not vanish entirely during flooding. A remotely operated vehicle descends toward the ridges. On camera, the largest face appears fractured and layered. The apparent blocks are connected to the rock behind them. Marine growth hides some joints, but the general structure agrees with the geological explanation. At the edge of the terrace, the smaller alignment looks different. Several stones rest above the surface rather than continuing into it. They are similar in size and lie close to a line that crosses the natural bedding at an angle. One has shifted, another is partly buried. No tool marks are visible through the growth. The robot follows the line beyond the frame shown in the original map. It ends after a short distance. There is no grand avenue, gate, or second row of buildings. Nearby sediment contains a few stone fragments and dark patches, but nothing can be identified from video alone. The result is layered. The sonar did not reveal a confirmed metropolis. Most of the apparent architecture is natural geology shaped by fracture, erosion, sediment, and the way the map was processed. Yet the survey has identified a preserved terrestrial surface beside an ancient channel and a small stone feature that does not fit the main geological pattern. The original interpretation was wrong in scale, but the location may still hold archaeology. This is a more difficult ending than confirmation or dismissal. The city has receded, while the human question has moved closer. One final set of samples must determine whether the short alignment belongs to natural movement, later disturbance, or deliberate placement on the drowned landscape. The short stone alignment now carries more weight than the walls that first drew attention. It is smaller, less dramatic, and harder to see. Yet because it rests above the ancient surface and crosses the natural bedding, it asks a question the larger ridges no longer ask. The vehicle returns with brighter lights and a camera positioned closer to the bottom. Several appear to come from material exposed nearby, so transport over a great distance is unlikely. No carved faces or clear tool marks appear. Still, the stones sit in more stable positions than loose fragments scattered by current. A core is taken beside the first stone. Another passes through sediment between the third and fourth. A comparison core is collected beyond the line. The samples reveal that the stones settled upon, or were placed upon, an old terrestrial surface before marine mud covered the area. Modern anchors and recent fishing activity are unlikely to explain the entire alignment. The feature is older than the upper marine layer, but age alone does not identify the cause. Ice, roots, slope failure, and erosion can also create short alignments. Geologists compare the feature with nearby deposits and find no exact duplicate, though several natural clusters share part of its pattern. The sediment between the stones contains a small concentration of charcoal and worked-looking flakes. Closer study shows that the layer has been disturbed. Burrowing animals and water movement have mixed material from slightly different depths. One flake displays clear human working, but its original position cannot be recovered with certainty. This is where the evidence stops before the city. The site now has repeatable sonar, direct visual confirmation, a preserved ancient land surface, a short arrangement of separate stones, and at least one human-made object from the surrounding sediment. It does not have a secure construction layer linking the artifact to the stones. It has no complete building plan, no floor, no hearth in place, no repeated rooms, and no wider settlement pattern. The most responsible description is cautious, possible human modification, or stone placement on a submerged prehistoric landscape. The phrase lacks the force of megalithic city, but it says exactly what the evidence can carry. An undisturbed charcoal patch beneath one stone could date placement. Additional worked material within a sealed layer could establish activity. More alignments might reveal a fish trap, boundary, shelter, marker, or working area. New cores could also show that the stones moved naturally before flooding. If deliberate placement is confirmed, the discovery would add a rare human feature to a drowned landscape from a period poorly represented in coastal archaeology. Its purpose could reveal fishing, navigation, gathering, ritual, or adaptation without requiring a lost urban empire. If natural processes explain the alignment, the preserved land surface remains valuable. It can guide future searches toward places where camps or activity areas may be buried beyond the small survey zone. The investigation would have found a landscape instead of a monument. This is the deeper reversal. Caution has not destroyed the mystery. It has separated a testable human question from an image that carried too much certainty. The original city was partly built by the eye, but the seabed still holds evidence worth protecting. The distinction also changes what success means. An expedition does not fail when a spectacular claim becomes smaller. It succeeds when the surviving conclusion is strong enough to support future work. The ocean may not be hiding the civilization imagined in legends. It is hiding versions of human life that land archaeology cannot recover alone. Their remains may be low, scattered, and difficult to name, yet they belong to the missing geography of our species. The final chapter must therefore leave the single alignment behind and look again at the shelves surrounding every continent. What has been proved is narrower than the title. What remains possible is larger than one city. The investigation began with a city shaped from sound. Long ridges became walls, shadows became streets, and an elevated terrace suggested a monument on land last exposed when the ocean stood lower. Sonar can restore river valleys beneath modern seas and guide robots toward features no diver would find by chance. But sonar does not name what it records. Architecture appears only when geometry is joined by construction, context, artifacts, and time. Vast areas of continental shelf were once dry. People could live, travel, gather, hunt, fish, bury their dead, and exchange knowledge across landscapes now represented only by blue. The ocean unquestionably covers part of the human record. Doggerland proves the scale of that loss. Rivers, wetlands, lakes, ridges, and plains once connected Britain with continental Europe. Yet the country beneath the North Sea also teaches that a lost human world does not need monumental cities to matter. Its low walls, streets, rooms, graves, and artifacts form a secure settlement plan. The remains are less visually overwhelming than some disputed formations, but their human origin is stronger because separate clues agree. They also belong to a period much later than the end of the Ice Age, proving that depth and antiquity cannot be treated as the same thing. Yonaguni shows how geology can rise into forms that feel designed. The Gulf of Kambat shows how ancient material, drowned landscapes, and geometric sonar can merge into a conclusion before their relationships are established. First, extensive prehistoric landscapes and human sites lie beneath the sea. Second, future exploration may reveal forms of coastal organization more complex than surviving land evidence suggests. Engineered shorelines, communal fish traps, gathering places, boat landings, ritual features, seasonal settlements, and perhaps larger centers may wait beneath preserved sediment. Such findings could change how migration, exchange, and social development are understood. Third, a sonar image alone does not prove a megalithic urban civilization older than the end of the Ice Age. An extraordinary claim of that scale requires repeated architecture, secure occupation layers, associated artifacts, reliable dates, and a wider cultural footprint. The evidence must connect stone, people, and time. The most promising targets may not be giant terraces exposed on the seabed. They may be ancient soils beneath smooth mud, buried riverbanks beside freshwater channels, or small stone arrangements whose meaning survives only in their relationship to surrounding layers. Algorithms reopen archives gathered for purposes unrelated to archaeology. Environmental evidence can rebuild landscapes from pollen, shell, chemistry, and genetic traces. With greater power comes a greater risk of premature certainty. More detailed maps will produce more convincing shapes. Images will travel faster than expeditions. A rectangle can become a city in public memory before the first core reaches the deck. The discipline of doubt must advance beside the technology. Somewhere on another continental shelf, a vehicle is moving through a routine grid. It may be surveying a future cable route, a wind project, a geological basin, or an area marked only by coordinates. Its sonar sends pulses downward and listens. Most returns describe ordinary seabed. A buried channel bends through sediment. A ridge follows the expected geology. Then a narrow line crosses an ancient terrace at an angle that does not immediately fit. The vehicle continues. No one aboard sees the feature as it is recorded. Weeks later, the data are opened on a quiet screen. The line appears again in the next pass. It may be natural, it may be modern, it may be the edge of a place where people once worked before the sea arrived. No responsible observer calls it a city. The coordinate is marked. Humanity has not lost only one Atlantis beneath the ocean. It has lost coastlines extending around the planet, each containing its own ordinary and extraordinary histories. Most will never return intact. Some may survive as scattered tools. Others may preserve floors, wood, graves, paths, or structures beneath protective mud. The search has only begun, and its greatest discovery may be a new understanding of what was lost, rather than proof of the legend expected at the beginning. The map is still being drawn, and somewhere beneath its unfinished lines, the next chapter of human history is waiting.